the time of the opening section number 1B. I am a chairman of this section. My name is Anatoly Klimov. I am from Moscow, Russia, and our local time 9:30. And main rule of our conference for any question, you must push hand. Only push hand is the signal for the question. The first presentation will be done Professor Iwamura from Japan. And please, Professor Iwamura, you can start your presentation.
Okay, thank you. Yasuhiro Iwamura of Tohoku University. I would like to talk about progress in energy generation research using nanometal with hydrogen or deuterium gas. As you know very well, this field started in 1989 with Fleischmann and Pons electrolysis of palladium with heavy water. But some researchers started make different experiments, gas rodding experiments. Denino and Scalmuti of Enia in Italy tried to detect neutron and proton from deuterated titanium. And according to the book edited by Jean-Paul Bebelian, Fralick of NASA firstly made an excess heat experiment using palladium and deuterium gas. And Lee and Bebelian also observed excess heat using the palladium and deuterium gas. And Piantelli and Fourcade in Italy firstly made experiments, excess heat experiment using nickel and hydrogen gas. Francisco Celani has been making by his original method, high voltage pulse to constant wire with hydrogen gas. And beryllium also, beryllium is attempting commercialize with their own method, Q-pulse, using a nickel and hydrogen gas. And these studies, these work did not specifically consider the nano-sized metal. But these research is based on the nano-sized metal or nanoscale material in addition to gas rod. Arata and Chan firstly made experiment using a palladium black with the deuterium gas. And Iwamura and Ito firstly made a transmutation experiment using nanofilm palladium and deuterium gas. And Mizuno and Kitamura Takahashi made further progress. And I would like to briefly introduce their research. This is Arata's experiment. He utilized the palladium black, palladium particles. And using this configuration, high pressure deuterium gas is generated by electrolysis of heavy water and absorbed by palladium black. And he observed a long-term excess heat production as shown in this figure. This is the time, and this axis is excess heat. And this is the line of 10 watts. And these arrows correspond to 20 days. So he observed a very long-term excess heat production. And next one is NEDO project. NEDO is a funding agency operated by Japanese government. And in this project, Technober and Nissan and Kobe University, Nagoya University, and Kyushu University and Tohoku University participated in this project. And they used this kind of nanomaterial, nanoparticle, mainly nickel and zirconia and copper and palladium. And they observed anomalous heat generation that cannot be explained by non-chemical reaction. And also they confirmed the reproducibility by conducting experiments at Kobe University and Tohoku University. Using same sample and the same conditions, they got same, almost similar results. Okay. And this figure shows recent research activity of our team. As I mentioned, I was involved in the permission-induced transmutation reactions with nano-sized multilayer thin film. This is a cross-sectional view of palladium nano-sized palladium film, multilayer thin film. And we use the palladium and the calcium oxide, and we put the cesium or barium that these elements we would like to transmute. And this surface area filled with D2 gas, and the other side is pumped up by turbomolecular pump. And then deuterium atom transmute through this multilayer thin film. And they observe this transmutation reaction of cesium into praseodymium like this. And we also have experienced excess energy experiments with nano-sized metal composite particles in the nano project or replication of a Mizuno experiment. And so we combining these elements, these factors. Recently, we have developed a new type of experimental method using a nano-sized nickel-based composite material. And we call it, recently, we call it the quantum hydrogen energy. Anyway, we got larger anomalous energy per hydrogen obtained. Recently, we have decided to refer this anomalous excess heat as a quantum hydrogen energy, QHE. QHE is defined as a heat release energy induced by quantum phenomena during the diffusion process in nano-sized metal composite with high density of hydrogen. Okay. So QHE is, I created this word for general public. Okay. This figure shows progress from the time of discovery and to the present. In the beginning, the significant difference between in 1989 and present in material and working temperature, operating temperature is significantly different. At first, in 1989, we were using a very expensive material, palladium and deuterium. But now we are using nickel and original hydrogen, and this is very low cost and cost effective now. And in the 1989, we are talking about the increased temperature around the room temperature. Okay, but now we are talking about the elevated temperature, about a few hundred degrees centigrade. So it enables us to use turbine to convert heat to power, and it will make impact on industrialization. Okay, so I'd like to introduce our experimental method. As I said, we usually use two nano-sized multilayer metal composites, two seeds. And the center, we have a ceramic heater. And at first, procedure is as follows. Now, at first, we introduce the sample into a chamber, vacuum chamber, and baking the sample to remove mainly water or carbon impurities. After that, a hydrogen gas is introduced into the chamber, and two samples get absorb hydrogen. And after that, we evacuate the hydrogen gas by turbomolecular form and simultaneously heat up the sample to trigger the anomalous heat effect. Okay. And we observe the excess heat, and we cool down the sample and repeat the process, this process. Okay. This is the photos of copper nickel multilayer thin film and experimental setup. This area corresponds to the nickel bulk, and on top, this is the copper nanofilm 2 nanometer and the nickel 14 nanometer. And this is the example of excess heat generation. This is the elapsed time, and the red circle corresponds to the excess power, and the blue point corresponds to the pressure in the chamber. At the beginning of the experiments, we introduce hydrogen is introduced into the chamber about 230 Pascal, and samples absorbed hydrogen gradually like this. And next day, we evacuate the hydrogen, and simultaneously we heat up the sample up to 800 degrees centigrade. And then we observe the excess power like this, excess power about the 5 watts. And after that, we switched off the heater, and after that, we introduce hydrogen again at this point, and gradually sample absorb. And next day, we change the experimental condition. In this case, input power is different, and we observe excess heat, and repeat this process. And according to the data, mainly pressure change, we can evaluate the absorbed hydrogen, number of hydrogen, okay? And we integrate the excess power, and we got the total excess energy, 1.1 megajoule. And we can calculate the excess energy per hydrogen. In this case, 16 kilo EV per hydrogen. Usually, chemical reaction in the range of electron volt. So 16 kilo EV per hydrogen is very large. Okay, after that, we introduce radiation thermometers to measure the surface temperature in addition to the thermocouple in the center. Okay. This slide explains the excess heat variation. As I said, we have 2 samples, and we have a ceramic heater here, and this is a chamber wall. And heat conduction term is here, and thermal radiation term is here, and input power, excess heat. And we can evaluate using this equation, excess heat. We perform the rank run using the same process with nickel bulk. And this chart, this figure shows the relation between the input power and some couple in the center of couple, some couple. This is the line of a blank run, and this is the line of a multilayer. And the excess heat is evaluated, calculated by the function of delta T. Delta T is the difference between multilayer and blank run. Okay. Okay. So I'd like to introduce a few examples. First one is heat burst example occurred on one side, six layers copper nickel multilayer composite. This is the elapsed time, and the excess power is vertical. Vertical axis means excess power. Changing the conditions, we observed excess power like this, and also we can observe a heat burst like this, many heat bursts like this, and expanding this heat burst is here. This is a heat burst, same one, and this is the elapsed time, and this one, red one is a temperature for some couple, the center of the heater, and blue one corresponds to the surface temperature A, and the green one corresponds to the surface temperature of B. At this time, we can see the sudden rapid temperature increase, and temperature about raise and increase about 15 degrees of centigrade, and after that some couple temperature gradually increase, but in this case not so much on the surface of ILA. So we can consider, in this case, heat burst phenomena occurred on surface B and propagate to the thermocouple and the surface A like this. Of course, during this time, input power and room temperature is almost constant. Okay, and next example is the heat burst occurred on both sides of multilayer composite. In this case, at this point, at this time, we can see the sudden increase of surface A here. And this heat burst propagate to the thermocouple, and after that, at this time, surface B, temperature of surface B rapidly increase. And this one is propagate here. Of course, for this case, room temperature and input power is constant. And we apply this data, very simple delay time analysis. This is a cross-sectional view of a heater and a sample. A heater is composed of Al2O3, and we have an insulator here, SiO2, and a nickel multilayer sample here. And we can estimate using physical property, for example, thermal conductivity and specific feed and something like that. And we can calculate simple calculation using this equation, delay time 36 seconds. And if we consider, we analyze the experimental data, delay time from surface to TC can be estimated 33, and the delay time from surface B to TC can be estimated as 46 seconds. So this one I agree with experimental results. Of course, our 3D heat analysis would give more confident results, I think. Okay, Next example is the heat burst induced by intentional change of input power. These two examples is different. This is example 1 and 2 are spontaneous heat bursts, but this one is an intentional change, intentional heat burst. Okay. At this point, we have 25.8 watt input power, and at this time, input power is slightly decreased, and accordingly, surface A and B and TC decrease accordingly. And at this point, we return the input power to the original value, and then after that, at first, gradually increase TC and A and B. However, at this point, surface temperature increases rapidly, and also for surface temperature A rapidly increase. So, and TC is going up, and also surface A and B increase. So surface temperatures A, B, and TC all increased even though input power was once reduced. Increases in surface A and B temperatures are larger and steeper than that of TC. Okay, so it means that heat burst energy generated at the surface A and B propagated to TC. Our team may perform another optical observation during heat generation. Professor Kasagi will talk about this topic on 11th June, and et.al. will present at the poster presentation. We measure the mid-IR, near IR, and visible light during heat generation. And I would like to briefly introduce, in this case, we measure the mid-IR from surface A, and this is the time, and the red one is some couple in the heater, and the green one is a mid-IR intensity, integrated from 0.23 to 0.41 electron volt. As you can see, TC and mid-IR seems synchronized, and this is a very reasonable and give us the confidence that the heat burst occurred on the surface. And this one is future scientific and technological challenges. I think, in my opinion, I would like to, identification. It is necessary to identify anomalous exothermic reactions. We do not know at present what kind of reactions occur for heat generation. And also, we should confirm the consistency between mass defect and generated total amount of heat. And I think that it will be necessary a super clean environment and very high sensitive trace analysis technology. And also, demonstration device for practical use is effective, and the theoretical explanation for anomalous heat phenomena, and more important, I think, public acceptance of the technology in this field. Okay, I would like to conclude. Anomalous heat using nanometal with hydrogen deuterium gas could become the technology against global warming if it would be commercialized. Research on anomalous heat generation induced by the interaction of the hydrogen and deuterium gas with nanometal was briefly reviewed. Among them, nano-sized nickel-based composite material began to attract attention from industry because of its abundance on Earth, lower cost, and its ability to react with hydrogen at several hundred degrees centigrade. Our team developed a new type of energy generation method using a nano-sized metal multilayer composite, and hydrogen gas. We started to call the generated energy quantum hydrogen energy. According to our experimental results, exothermic reactions that cannot be explained by chemical reactions were observed in copper-nickel and copper-nickel multilayer metal composite. Maximum amount of heat generation was 16 keV per hydrogen. Not only steady-state heat generation, but also heat burst phenomena were observed. Experimental data analysis show that the exothermic reaction occurred near the surface. Recently, intentional heat burst has become possible. By measuring the optical spectrum emitted from the sample, we detected simultaneously increase in radiation flux when the heat burst occurred. Future scientific and technological challenges in this field were discussed. This emerging technology is expected to be commercially feasible. Thank you for attention. Oh, so that's it. And this is
Thank you, Professor Iwamura, for very interesting presentation. We have small time for any questions. Very short question, please. Please, Luciana Onder.
Please, Dr. Iwamura, do you think that neutrons, background neutrons, could be causing these spikes in the excess heat?
You were talking about the neutron?
Yes, yes, background neutrons.
We usually observe the neutron, but we did not significant increase of neutron.
Thank you. Very good answer. And Chertsky, please.
Thank you very much for a very nice talk, Professor Iwamura. I would like to ask you about comparison between hydrogen-induced reaction and neutron-induced reactions. You have measured in the past also some experiments with deuterium gas. So what kind of differences, power differences, temperature differences you could observe?
In our experiments, we concentrate in hydrogen only. So we did not perform the deuterium gas experiment. And another question is about the mass spectrum. Or
no, there's a question because in the past you observed also heat excess using deuterium gas. And the question was, what is the difference in the power